that. Okay, so the algebra of vectors. Okay, so the abstract n-dimensional spaces are strings of points, okay, and strings of endpoints, okay, and then to get to the next level, we introduce vectors, and they also happen to be strings of n numbers, okay. So that way we can do whichever we want, either one or the other. We already did the geometry. Geometry. This is where geometry is. And for the time being, there is no geometry of vectors just yet. So we start with vector algebra. Okay, so the as simple as it gets, the algebra is very simple. It's just done component wise. Okay, so you line the components and do the algebra within each of them separately, as if they were just they are numbers. So just never mixing x's with y's and y's with z's. Okay, so once you do this, we done plenty of that in dimension 2. Now dimension 3 is right here. Align whichever notation you prefer, brackets or columns. They're still aligned. So as long as they align, you can carry out that operation. So naturally, the one is this slightly more compact, especially when you write it out for a dimension n. But it remains the same. The only thing is that you have that dot thing. Okay, so if you were to worry about the pattern there, so you have a special kind of vector, then maybe you have to so it's a sequence after all. So if you know the one sequence, the other sequence, you can add them. You did that in calculus. It's just the same as adding functions. And then it's an issue of notation really. So the endpoints are added together. The endpoints of those vectors, they're given as points on the left. Then we're forgetting that. So that's we're moving on, which is better just not to speak of points at all, as much as only when necessary. No points anymore. As you can see, names of a single name is given to every vector. And again, addition is just component wise. If you want to visualize, there is no way you can visualize 20-dimensional space in any reasonable way. So that's the only way I can suggest. Once again, going back to whatever you learn possibly in calculus, and that's algebraic operations with functions. The simplest function, or one of the simplest functions, is the sequence, and that's what they look like. And once again, if you know algebra functions, this is the algebra vector. So really not. It's actually simpler, obviously. The geometry once again, not geometry, but rather visualization of that addition is here. So the sequence is one, the bars, and the sequence of the other one, another set of bars. They align. Okay, so they're never they align on the right, and then you take the lengths would be negative of all those bars that we have produced, and that's my new sequence. Okay. So scale multiplication, the second operation, is once again component wise. There is nothing to align anymore, but nonetheless you're going along the components. Each component is multiplied by that number. Either you go vertically or horizontally, makes absolutely no difference. Once again, we abandon the points as we're moving on to pure vector algebra. Okay, so once again, component wise, everyone is multiplied. If you were to once again go back to calculus, pre-calculus, it's multiplication of sequences. And that's every bar is stretched. Okay, every bar is stretched, and that's unit vector. That's all there is. Naturally, this kind of it does look familiar. I hope that kind of a stretching of those bars. Stretching, if it was a curve, the curve would be entirely stretched in the vertical direction. But it only keep in mind that this is better than it looks. Wait a minute, it's not as good as it looks. Because this only makes sense. You kind of can see either this example or that example. You can see a curve. Implicitly, there's a curve there, and you add them together. But naturally, there is no restriction on our vectors. Any combination of n numbers is possible. So generally speaking, a sequence would look like entirely up and down in some random way. Okay, so that's what the vector looks like. So this is just so you can see a pattern of addition. Okay. So anyway, so why so? That's an example of if we were to share to do, for example, the simplest operations is to add together to merge together two portfolios, and then every single stock or bond, doesn't matter, is there, and then we're doing, as you can see, I switch from dollars to number of shares to make a point, and the point is that there is no homogeneity about the each entry. We're doing it, that perfectly matches what the algebra that we do, is that we do not intermix them. So even though the share of Apple and the share of whatever Ford, they have very different prices. So it doesn't matter. You cannot mix them together. You cannot add one, just like you don't add apples to oranges. You don't add a share of Ford to share of Amazon. Okay, so because they're literally priced dollars per share, and share of Amazon is literally not the same as share of Ford. So fortunately, everything is designed in such a way that it doesn't matter. You just merge them, you add them together one at a time. Okay, so whether if you're willing later on to find out what's the value of my total portfolio, that's fine, but we don't need to add dollars. Okay, we adding shares. So all of these counts are a number of shares. Okay, so and then that's Excel. That's literally how they would be doing over in on Wall Street. They use Excel a lot. Okay, so doubling, tripling portfolio. Suppose you have a perfectly balanced portfolio in terms of stocks and bonds and commodities, whatever you want, and then you want to just the same, only twice as big. Wow, there you go. You just multiply everything by 2. Once again, it's not multiplication of dollars. This is once again number of shares. And some of them are shares, some of them are not even shares. Maybe you are literally trading in gold, literally. So then those are pounds and whatever the gold is measured in. What is the unit of gold?
Is it ounces?
What?
Is it
ounces? Yes, ounces, right, per ounce. So totally possible. So that once again, the algebra is perfectly all right. There is no trouble. So this is the bottom is a typical example. If you also throw in a bunch of different currencies, once again, they're not intermixed, and unless you start trading them, well, there's no need to know what 1 yen, how many dollars that is. Okay, so for the record, these are the two operations on our vectors in the dimensions, string of n numbers, 2 strings added together component-wise, or scalar multiplication multiplied by that real number, including -1. Okay, so dimension doesn't matter anymore. Okay, so once again, addition. So there are some special circumstances, such as special vectors. The 0 vector. Okay, so that's your 0 portfolio, if you like. And then there's a negative vector for each vector, and there's a negative vector. You just take negative of each of them. Okay, so the specials they go into special places. So decomposition. Then again, we already I think we did this before. So we do decomposition again. So once again, if we don't have axes, if we don't have units, so then what do we do? That's what we do. We can express. Still, we can reduce everything to the building blocks, and those building blocks are the unit vectors along these two, in this case, 2 axes. Well, not axes, but the two vectors in terms of which we can express everything. So in this case, it's 1, 0, 0, 1. Once again, angles or distances, for that matter, don't matter. So we just visualize with perpendicular axis, but makes no difference. The algebra works out perfectly well if their angle is different, and it is just a habit, because once again, homogeneous. If there is no homogeneity, and you were to plot, why would you say that these vectors are perpendicular to each other? They even have different units. Okay, so you can't really do algebra with. So this is Ford and this is Amazon, whatever, or Apple. What's the doesn't matter. Apple. So then they're not perpendicular because there is no distance. There is no distance. There is no geometry. There are no angles, and there are no perpendicularity if within this space. So we're talking about the space of stocks bonds, for example. So once again, the totally inhomogeneous, non-homogeneous directions, and therefore we don't have any geometry, and therefore there is no such thing as an angle. Okay. So we just, for our convenience, we do what we have been doing in lower dimensions. We present them as perpendicular. Okay, but that's just a matter of convenience. As you can see, if you start, let me, as a matter of fact, make that point clear. The vector is on the left, and I want to decompose it into some vectors that are simpler. So the end result is right here, as a matter of fact. So the vector is drawn. Then at the origin, I draw two. This probably could have been a starting point rather than the ending point. So I have a blue vector. No, starting point is, so that's stage 2. That's the start is here. That's the start. Then this will be the first stage of your analysis might be if you were doing geometry, obviously. 3D space or 2D space, so physical space. Physical space, if it was physical space, then you would proceed here. You would give it what, either grid or axes, or in this case, you give it basis vector. So once again, in the grid for both of them, and then what you do, you express that vector that you're concerned about in terms of those two, red and green. Okay, so this is exactly what this is. 1, 0, 0, 1, and so the end result is this. Well, this is the end result. This is what we have discovered. So if it is a physical space, if it's not a physical space, then there is no such thing. So that's a physical space. If it's not, if it's the space is already abstract, you already have, and you cannot not have the grid. So the grid is already there. So then it is not even a matter of decomposition. And hypothetically, unless we do something about it, there is no alternatives. This one has totally alternative. Right? If we put axes like this, and they don't have to be perpendicular at all. So maybe why not? This is a if I want to code 1, 0, I do, and this is 0, 1. Okay, and so there is nothing wrong from these the two building blocks that I start with, and I can construct the rest of them will work out the same, except the numbers will be different. So that's the thing about physical space. It's our choice to create the axes the way we like, and the basis vector the way we like. In abstract space, it's not a choice anymore, but hypothetically, we could still come up with it if we really want to. Sometimes we do. But initially, it's nothing. Everything is fixed, written in stone. So the components are given. It's literally, they're not components. You don't decompose literally. The numbers are already there. Okay. So this is decomposition is very simple. So once the components are supplied, they are literally, look at them. Those components A and B in dimension 1 are literally the coefficients of the basis vectors right there. Okay, so A and B, this is A and this is B. Okay, so that's the meaning of our components. They're literally how much of the first vector we take and how much of the second vector we take, and then bring them together. So both on the left we have components, on the right we have the combination of the two of the two algebraic operations of vectors. We have both a scalar multiplication, I and j are the vectors, and then we do addition. Okay, so this is decomposition already. So I think we've seen this before. Okay, so once again, decompose the vector into I and j, for 1, same exact numbers. In dimension 3, you have 3 basis vectors. Once again, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so they're harder to depict, but nonetheless, they're right here. So it's a box with its dimension visible, and then once again, the meaning of A, B, and C are these 3 vectors. How much of each of these vectors we take, how much we progress in each of these directions, so that gives me altogether the whole vector. In dimension n, the same story. You have to just think n-dimensionally. So once again, there are basis vectors. There are n of them, and each of them has a one single one among zeros. Okay, so these are n basis vectors, and once again, the story is exactly the same. So if we understand early dimension 2, dimension 3, we know there is nothing new to us here, which is that's the decomposition. So we have vectors E1 through En, okay, and then what E stands for? Maybe elementary, like elementary blocks, or something like that. So E1 through En, and so these are the vectors, and then vectors, and then here I don't follow my own rule of using the capitalization for vectors and using lowercase for the numbers. But so that's why it might look more confusing than it should. So x's are numbers and e's are vectors. Okay, but so we have a bunch of operations. Don't forget the once again notation that I bring it up all the time. It's called a linear combination. So you have a bunch of vectors and then you give them coefficients and they add them together. That's a linear combination. It will become more important. So, okay, once again, system it comes with axes, and here we have the origin and the basis vectors. Once again, we've seen this before. Slightly different angle. So basis, we are studying the sliding object on a slope, and then we basis vectors are naturally go with the horizontal and vertical. The force, after all, is vertical. But if you were to simplify motion, representation of your motion mathematically, you might realize that actually the slope is actually is the direct. It cannot not move along the slope. So let's pick that one as one of the basis vectors, and then the change of the basis is what is happening here. Standard basis, and then new basis. Data basis, and that's you must have seen change of basis is the same as change of variables. Remember change of variables that you do in calculus quite a bit by means of we looked into that. Remember, so how do we do change of variables? What's the mathematical tool for change of variables, change of units? Same story. What's the mathematical tool? Well, the answer is the composition. So you have a conversion formula for the units, and then you have that. What that creates is it's a function, and that function is to be substituted into whatever you've got. Maybe you have a whole dynamics worked out, and then you substitute that formula, and you have a dynamics with respect to the new unit, or in this case, the new variable or variables. In which case, the whole story changes because not it's not one variable at a time, but in this case, two variables together, and therefore the change of those units will be highly non-trivial, which is the point. So then the red one becomes, it's not that it is irrelevant, it is zero at all times. Okay, and so it simplifies the two-dimensional motion becomes one-dimensional because it is. If you cannot leave the slope that incline, then it is one-dimensional. So if you choose your directions wisely, then that the only direction, then the purple one that you'll have to take care of. So that's the way to study things that are possibly they don't look as they look familiar, but if there is some pattern to it, maybe symmetry too, that you can utilize. That's how you do it. So that's my direction. It is one-dimensional motion, as you can see. Well, you can imagine what happens on the slope. Well, if your slope is variable, then you have to look at the tangent lines one at a time. But nonetheless, it still works out. Can be made worked out. Okay, so an alternative. By the way, here have we started to speak of geometry here? And we are starting to speak of geometry here because perpendicularity here matters. But once again, in the physical space, it matters in the because the physical space has a geometry there, And then what about abstract spaces? Abstract spaces. So we do have geometry in abstract spaces. So once I'm back to my space of stocks. Okay, so this one I'm taking two-dimensional stock to actually compare these two examples. So we just split stocks and bonds. Okay, stocks and bonds, and some advisor told you that it's perfect to have stocks to bonds for your particular situation, 1-2. So you have twice as much money in the bonds than in the stocks. Okay, so why not? And then naturally, then once again, that's the advice. Okay, so that's the advice, but really this the space comes first. The space is of two numbers. The first number is the amount of stocks, the other one of bonds, and then every point on the plane, not the whole plane, but positive plane only, gives you the various portfolios. Okay, so all possible portfolios are there. So looking like this. So naturally, these are the X's, these are the stocks, stocks, and these are the bonds, Y bonds. And so once again, the first quadrant are the actual portfolios. Now suppose that's the advice. We take it for granted that it is correct. Okay, so we want to evaluate how well portfolios follow this advice. Okay, so one way to do it is to realize that the perfect portfolios follow this vector to 1, 2, 1, 2. The amount of there's twice as much of stocks than bonds. Am I doing the opposite here? Stocks and bonds is 1 to 2 to 2. So it sounds like there's a. Which one is the first one? Which is the second one? Stocks first. Y bonds second, and therefore. I think my algebra here is okay. Let's okay. So I wrote stocks come first, bonds come second. Okay. So the opposite. So there are not the opposite. There are twice as much bonds than stocks. Okay. This vector is not 1, 2. It should be 2, 1. Not 2, 1. It should be 1, 2. Right. 1, 2. There are bonds. More bonds than stocks. Right. So this is all. Okay. So the perfect portfolios are along this line. These are perfect. Okay, 2, 1 stocks, bonds, and there are twice as much bonds than stocks. Okay, and so, but what about the rest of the points? You can try to evaluate how close you are to the perfection, and that's where the yellow matters. You say so. The ideally, the blue vector is in fact how far you are from the perfect. So what is you are here? So I'm here. That's my portfolio. This is ideal. And then how do I know how close I am to the perfection? That's the way to go. Okay, so perpendicular. So perpendicularity is what probably nearest. You are looking for the nearest perfect portfolio. In fact, it's not even how far you are. The question is how to get to it, to the ideal situation. And the answer is go perpendicular, the shortest distance perpendicular. So that's line, and you go towards it. So that's why, incidentally, we're going to need the geometry eventually, even for these abstract spaces. There's a need for geometry. This only works out because this is, and I don't want to hide it from you, this is homogeneous. Look at it. You cannot compare stocks and bonds unless you express them in the same terms. In this case, they are both in dollars. Okay, so I made a big point about it with this algebra that we did over here. Is you do not know, do you have to intermix the different stocks, nor currencies, nor commodities, right? And then, so because it works out perfectly, because it's algebra. But once we get to geometry, okay, so we are asking how close we are to something, for example. Then we have to have some kind of homogeneity to the directions. And if you were to speak of portfolios, then you say just let's express them in dollars, okay? So which naturally the problem is not, it does not come easily because then what you end up with is then if the prices change, then your assessment changes automatically daily or 1 second a second at a time because like I said, the prices change, and so your portfolio the balance also changes automatically every day because this is the advice is expressed in terms of dollars, not in terms of the number of stocks and number of bonds. So anyway, but the point here is, suppose we do have we do it homogeneously. We have dollars for each. Then the angles make sense. Distances make sense too. We don't have to invent anything because that's on the plane. And then yeah. So that's the idea. How do I get to the perfect portfolio? And the answer is I go perpendicularly towards it, and that's why the decomposition of our vectors would make sense with one vector going towards along the perfect line, the purple one, and the other one is perpendicular. That is the blue one. It is how far we are from the perfection. Okay, so that's literally the purple one. Everything is fine, and the blue one is actually what we care about. It will tell us how well we're doing and which way we should proceed in order to fix the problem that we have. So naturally, you can imagine what happens in high dimension. Okay, any questions about this? So no algebra just yet. Sorry, no geometry. Okay, so we'll continue on with algebra. So this is geometry necessary in this particular case, but it's just a good example because we have still the decomposition. The decomposition is the point that I wanna make again is the decomposition of every portfolio literally is decomposed. It's not decomposed. Look at it. Initially, every portfolio is decomposed into stocks plus bonds, right? That's the original decomposition. But what we might be interested in the light of this advice is that let's decompose it very differently. The one-to-one combination of stocks and bonds, and whatever is the excess to that. Okay, so that's something that has to be sold and bought and trade stocks for bonds in order to make it perfect. So that's still a valuable idea here for algebra, not for geometry. Okay, more algebra. So let's take a look. So we need to reassess the algebra as we know it. Okay, so to understand the algebra of vectors, we need to understand the algebra of numbers. Okay, so we are so used to it, we have done it for literally decades, so we are not thinking about it twice, and we need to rethink. Okay, in what sense? In this sense, we have to look at the law of development. Okay, if we wanted to progress from numbers to vectors, we need to understand what survives this transition. It is a big transition as we are facing, and then what things will still be there and which one will not. Okay, so let me point out what naturally survives. Naturally, what survives are the laws, as I said, but there are certain things that the vectors do not have. Number one is, for example, what not is order. Okay, x less than y. There is no such thing anymore. Okay, and secondly, for now, geometry. So later on, we will get started with geometry in multidimensional spaces. But at this point, if we speak of algebra, geometry is out. So, for example, there is no such thing as small or big or far or close, nothing like that. But so laws of algebra, and so we ignore the dot products until we get back to geometry. And then here's the distributive property of numbers that we're so familiar with, and we just see if it survives is it possible to have it for vectors? And here, once again, we have to very carefully one at a time because the operations have the same notation, but they're not the same. So addition is not we add vectors, and we can also add numbers, but we can multiply the numbers, but we cannot multiply vectors at this time. So here, if you were to look at this and ask yourself, can this be about vectors? And the answer is yes, but then x cannot be a vector. Okay, y and z could be vectors, but x cannot be. So can we distribute literally as what the property says? Can you distribute x over addition? And the answer is yes. Just this I'm putting it where I think yeah. So I hold on. Actually, I don't know. Actually, you can do both ways. You can have y, z. But the simplest version of this formula for in the vector algebra is x. If x is a vector, you multiply it by y plus z. Once again, lowercase. These are numbers. And is this true? So from the numbers, I'm making this step towards vectors, and I can just cast it very easily and realize that yes, 3, 4 multiplied by 2 plus 5. Okay, and then I first multiply by 7, which gives me 21, 28. Okay, and I do the alternative. So the left-hand side gives me 21, 28. But the right-hand side, if I multiply 3, 4 by 2, and then multiply 3, 4 by 5 right here. So, and then add it together. So the answer is still 21, 28. So it checks out. Okay, so it works out. This is, at least in this example, the distributive property works for vectors. So not too bad. And this is the other version. So that's I guess one thing to pay attention to is that it's not that is there a distributive property? Yes, there is. There are two of them. Okay, so once again, which one you choose? You cannot choose x, y, and z, all three of them to be vectors, but if you choose either one or the other to be vectors, then it works out. So either we choose x to be a vector, or we choose y and z to be vectors. So that's the same property. Okay, same. If there were numbers, it looks exactly the same, but I'm capitalizing y and z, indicating that it's vectors, and it's a definitely different vectors, a different formula. And but then verification once again. I don't want to spend too much time, but it checks out. Once again, so scale multiplication, I'm sorry, scale multiplication and addition, as you can see, you add first and then multiply by 2 or vice versa. I must have a diagram here, but let's, so say x, y, okay, so I add them, x plus y, okay, and then multiply by k. So I have k, I have what? Kx plus 1. Okay, so that's one route. And the other route is first multiply by k, which gives me kx, ky, and then I add them together. So I have kx plus ky. Okay, and the answer is the same. Same with same with the other one. So this one is a bit simpler. So, but it's same idea as a matter of fact. But let me do it. So I have y, z, and then I multiply by x. Okay, so which gives me x, y, xz, and then I can add them together. And so once again, I can have two routes. Using this interest. So the diagrams, the examples, the algebra is quite predictable. You can that's what the first distributive property looks like. Once again, written in vectors. If you don't know that A stands for capitalization stands for vectors, you wouldn't think it is a very familiar distributive property of algebra of numbers. And then once again, you can see it in vectors. If this doesn't convince you, addition component wise and multiplication component wise, look at what it means for vectors that we do in geometry. Okay, so what does it mean to double a vector? You just do it twice. What means it for a triple a vector? Once again, you just triple them. Okay, so that dimension 1, and then if you do the same, that's what scale multiplication does. Doesn't matter which way they're pointing this way, and that's the algebra that is happening. This is the algebra. This is the first. Hold on. Yeah, the first distributive property. Okay, so two, double, triple, or 2 plus 3. So the result is the same. So the algebra that I did up there, I'm doing here geometrically, naturally it's the same vector. And then what about high dimension? That's one dimensional where vectors are numbers. Okay, so it's easy. But if you go to high dimension, what's the difference? So if it's like this or it's like that, it's the same diagram, right? So there is no difference. And then that's the thing about scale multiplication is that the direction doesn't change. So if it was the story was one dimensional, in high dimension, it's still one dimensional. So even if you go to 50 dimensional space, it still will be one dimensional, and the diagram holds. And therefore, yeah, we conclude that indeed the first distributive property, this one holds, and so we can use it freely anytime we do vector algebra. The second distributive property is this. Okay, so there's two vectors, one number. So it was two numbers, one vector, and here we have one number, two vectors. So the whatever is being factored out. So here we factored out the vector. Here we're factoring out the number. Okay, but so that's the difference. And once again, or if we go backwards, we distribute the number among the vectors. Okay, so this is addition. Once again, one-dimensional story is easy because addition is head to toe, and they do not change direction in one dimension. Okay, and so dimension two is more complicated, but once again we can see this is it illustrates the picture illustrates what I just talked about. So you do addition of the two vectors first, and then you double. Okay, so that's what you see on the left, or you double first and then add it together. Okay, so once again that little diagram, and then naturally you can see it's the picture at the bottom is just meant to point out that that it's the vector on the left and the vector on the right are the same. Okay, so if you just build a big parallelogram and cut it into 4 smaller parallelograms, and then you see the original addition on the left, you see the new addition on the right, and they are fit together perfectly well, producing the same result. You can make the same argument with not the same, but similar argument with dimension. So once again, that's the same operation, illustrating pretty much the same thing, but computationally. Okay, so the computations are here. They executed component-wise as by design. Okay, and then they just accompanied by illustration. So that's what produces pictures, but there is nothing tricky here. Okay, so the 40-dimensional spaces. Okay, so once again, if you are not convinced by these two-dimensional situation, why would it still be true in high dimensions when there are no arrows? We cannot speak of velocities or anything or forces like that. So you can just carry out a few examples, and you surely will convince yourself that works out perfectly well. So what is it? So look at on the left. So the left-hand side and the right-hand side illustrate here. This is left and this is right. So on the left, I have the vectors U and V, green and red at the bottom. Okay, and then I have the together. That's the first purple line, and then I double. Okay, so that's I'm progressing from bottom to top, left to right, and bottom to top. And so green and red added together produces the purple one, and then it's doubled. You can see how it's been doubled. On the other hand, I'm taking the same U and V are the same here and there. Okay. U and V are the same, but I'm doing different things on the different thing on the right. I double them first, and then add them together. So red, the second red is doubled. Green, the second green is doubled, and then add them together, producing the blue one. And as you can see, the blue one on the right, and the purple one at the top on the left are the same. Okay, so the building blocks are the same initially. Then you go through 2 intermediate steps, and then but the end result is still the same. Okay. If you needed any convincing, more convincing here. So the two, once again, two distributive property. Commutativity property is very easy. Once again, x plus y is equal to y plus x. We're using it without thinking. This is the illustration in dimension 2. Why it's true, you go left, you go right. Which one? A, then B, or B, then A. It makes no difference. 2 different triangles, but the parallelogram that produces the same, and so we have the same. We have the same outcome. So literally A plus B, I put replacing lowercase over here with uppercase here, and that's giving me commutative property, which we once again are free to use. So these are computations you can do with Excel. Associativity property, where there is an addition only. That's one of the simpler ones. So this is probably the simplest property. This is also it's simple. So as you can see, there's a difference to worry about. A, you add b plus c first, and then you add a, or you do a plus b and then c. So that's the difference. But fortunately, once again, everything works out perfectly well. So that's the associativity. The distributivity property of a dash of multiplication. Okay, so that's the distributivity property of a multiplication. And then do we have it? Do we have a similar property for multiplication? Is once again, not among vectors only. Okay, so one of these must be a vector. Okay, so either, but you cannot have two because we are not multiplying vectors right now, so you cannot have multiplication of two vectors, which means that of those three participants, one of them has to have to be a vector. So we choose to be C. Okay, so in other words, you think about what's about. You take C, you stretch it, and then you stretch it again. Okay, or so what's hold on, that's my writing here is wrong. What I meant here is A, B, C. Okay. So it's a typo. Okay, so you stretch by B, you C is a vector, you stretch by B and then you stretch by C. Or you first multiply A and B and then stretch. Okay, naturally you can get that the answer is the same. You can discover it right here with vectors or stretching of the that's what I just said. Stretching of the vectors multi dimensions. If I don't have it here because it's you must have done it before with vectors with functions. Okay, so special numbers 0 and 1. Okay, so this is what makes a number 0 special. 0 plus x is equal to x, 0 times x is equal to 0, 1 plus x is equal to x. And since we do not have, so the question becomes, is 0, we are generalizing this. Okay, so what is it 0? Is it a vector, is a number? Well, obviously it should be a number because there is nothing, well, looking at the first one, is 0 a number? And the answer is no, it's a vector. So 0 vector, we know that's what it looks like. This is a 4-dimensional space. What the 0 looks like, bunch of zeros. Okay, and then if you start adding it to anything, naturally this will still hold. So 0 plus x, and then putting capital letter here will give you an x. Okay, once again, component-wise, there is no difference. But this one is different, right? Here 0 could be x could be a vector and the 0 could be a number, and so that's what this is. When you multiply a vector by 0, you have a 0 vector. So this is it looks kind of simple algebra, but the reality is actually 0 on the left and 0 on the right is not the same. 0 on the left is a number, 0 on the right is a vector. Okay, so vector A is a vector. It's multiplied by 0, which is a number. The end result of the vector just happens to be 0, and so that's the confusing part sometimes. But the context usually makes it unambiguous. And so once again, on the right, it must be a vector. If you know that A is a vector, then whatever is on the right must be also a vector. Okay, so this is 0 vector. Okay, well, you can multiply a vector by 1, gives you the same vector. Negative vector, you multiply by -1. That's here it is. So what happens to a vector when you multiply by -1? Direction changes to the opposite. So I have four example vectors on the left. I multiply by -1, and there are a bunch of them pointing in the exact opposite direction with the same magnitude. Okay, and this is what happens in dimension 40. I multiply by -1, it flips vertically. And that's also, if you pick a random rather than a curve, that's what a vector in dimension 40 looks like. Okay, I just flip it. And so it points all the numbers, whichever was positive has become negative. That's what it is. Now this it looks long. I have to admit, this is we call them the axioms of a vector space. And there are a total of 8 of them, as you can see. So we talked about, we have talked about all of them. And so commutativity is simple in the beginning, then you have associativity, also simple. The second one, the third one is that 0 vector, the negative vector, the associativity for a scalar multiplication, then 1x is equal to x, and then we have at the end we have 7 and 8, two distributive properties of vector algebra. So altogether it's 8. Okay, so too many, and then naturally it's pretty hard to remember, and you might throw in some more if you just a shortcut. Fortunately, there is a rule of thumb. Okay, so if you just you eventually learn how to use it. So all manipulations of algebraic expressions that have done with numbers are now allowed with vectors as long as each of the expressions makes sense. Okay, so you're not going to do this because there's no division of vectors. Okay, but this one, so this is a no, but this one is a yes. Okay, because it makes sense. It makes sense, meaning that you can add vectors. So what's A? This one is a no. Because one is a number, A is a vector. Okay, so as you look at examine that expression that you have, as long as you start it correctly, then you can manipulate it as if you were manipulating numbers, and you'll be fine. So just as long as this was before you start doing anything, it was wrong to begin with. Okay, so if you start at the right place, then you do your manipulation just the way you did it in middle school, and then you end up where you everything will be fine. That's the rule of thumb. Okay. So, and that's sometimes called a vector space. Anything that satisfy these properties will be called a vector space, and that's separate. That's a big issue in linear algebra. So, in addition to multidimensional spaces, Rn spaces of functions, these could be infinite dimensional spaces. So there is more to it than this. So these eight axioms are quite important. As a matter of fact, if you want to go beyond Rn, then that's when you start using them directly rather than just a list of properties. V will be the starting point. Okay. Vector space, subspace, also that's going to be important. It is, and why we have that definition still in our hand, because Rn is, we think we kind of understand what Rn is, right? So it's made of points, and that's also is made of vectors. We do algebra component-wise. If we can execute no trouble just doing component-wise, everything is fine. Then if we do not components explicitly given that that's how we can do it, we use the eight axioms. Okay, so that's fine, but then there are subspaces. Okay, so as we have seen it just a minute ago, this is my R2, and then remember this one. Okay, this is a subspace. It is actually one-dimensional subspace inside of the two-dimensional space. So we never have really these spaces living apart from each other. So they're always they're connected by functions. At its simplest, they are simply subsets of each other. So you have a bunch of subsets and therefore subspaces of R2. Okay, so that's another copy of R1 passing through the origin, meaning what? You can do algebra within the red line as if it is a space. It's as if they were numbers. It's one-dimensional, even though it lives in the inside of the two-dimensional space, but nonetheless, it's one-dimensional. Therefore, these vectors, the red vectors, are in fact nothing like numbers. So if I have this vector and I have that vector, and I can add them together if I want to. And then what's going to happen? They will still within that vector. Okay, so that's the geometry that makes sense, just the way we did it with the stocks and bonds example. We did it with a slope as well. So let's look at the look at the algebra. X and y axis to begin with. These are complicated examples. I started with complicated examples. The simplest examples of subspaces of R2 are the axes. Okay, and they happen to be one-dimensional. Okay, so so when you start doing algebra with vectors that lie in the x-axis, I'm adding them together. What's going to happen when I add them? I will produce a new vector which also is within the x-axis. Okay, so if the y coordinate component is 0, like here, then no addition or scalar multiplication will produce the number that is non-zero. So the algebra is totally limited to the x-axis. Okay, and same thing with the y-axis. If the x-coordinate is 0, then it will never reappear. Therefore, all the algebra will stay within the vertical. Okay, so here's the that's the subspace, and they are really nothing but as if these operations are purely operations on the real numbers, because only the x component or the y component respectively is in play, and therefore it's a number. So one number at a time. Can we have higher? Can we have? Do we have more? So once again, we speak of subspaces of R2. Okay, so these the simplest examples, and there are more. But here's look at this once again. One, the diagonal 45-degree diagonal when x is equal to y. So this is how you can represent it. Okay, every point on the diagonal has the same components for x and y. Therefore, let's call them t. Once you call it, then you can start doing algebra with those vectors, the vectors that go diagonally, and then the end result is the same. Once again, a vector that goes along diagonal. So if these were equal to each other and those are equal to each other, you add them together component-wise, they're still equal to each other, which means that you're still within that line, and these are once again equal to each other. These are equal to each other. So these stay in this space S, let's call it. Okay. So then vector algebra actually, a bigger space produces vector algebra over a smaller space. But we know that what's important is that we never leave once we're doing all the algebra that subspace that's what makes us subspace a subspace. So these are the examples that I showed you. Any line that you draw through the origin will give you a one-dimensional subspace on the plane. Okay, the space that is not, this is not a subspace. The example on the right, as you can see, if the line does not pass through the origin, you can see that adding of two vectors, I take those two green vectors, add them together. Okay, so the ends of those vectors lie on this line. So right here and right there. But when they add them together, the end result is not in S. So if your line is passing through the origin, then adding vectors will do this. Okay, multiplying the same thing. But if it is not passing through the origin, this is my origin right here. Adding these two vectors will not produce a vector that's still within the S. Same with scale multiplication. That's very much what we expect to have with subspaces. Okay, so in high dimensions, you can guess. So these are one-dimensional subspaces of R2. You can have them also in R3. Okay, in exactly the same manner. If I were to move on to R3, still take us go the same way. Go with the v-axis first. So we have three axes, each of which is a subspace. Okay, you can go diagonal of a variety of lines passing through the origin. They all will be subspaces. The question is really, are there any subspaces that are dimension 2? So three-dimensional space, can you think of subspaces of dimension 2? So in other words, a plane. After all, what is a two-dimensional space? It's a plane, and so we just need to find planes in R3 that are subspaces. And once again, by the same logic, not all of them are. Okay, so do we need those subspaces, which once we start doing algebra within them, will never leave. Okay, so these are kind of a self-contained thing. So they're just as good at vector spaces as the original one. They just happen to be inside of another one. So that's the only difference. And once again, those examples you can see here. So the logic is roughly the same. You start with the coordinate planes. X, Y, Y, Z, and Z X planes will be subspaces because once again, by the same logic, if say the Z coordinate is equal to 0, right? Think about it. If the Z coordinate is equal to 0, then you are here on the plane, and then the algebra on that plane will stay within the plane. And so once again, you have a plane of vectors, and that plane of all the algebra as if. Even though we execute it in R3, but the third coordinate is really not contributing anything because it's always 0. And so we are good to go like we have a space of vectors. So that's the logic that's in n-dimensional space. Here I'm giving you an example of how the space, the biggest space, smaller subset. If you choose your S carefully, then the addition is carried out as if it is actually n minus one dimensional space, because the last dimension is zero, so 0 plus 0 equal to 0, so the algebra is that last coordinate does not contribute anything. So it is actually S is as if it was R n minus 1, okay, so lower dimension space. You can check it with scale multiplication as well. Okay, so what we describe it is a closeness, which I view I try to explain it in a number of ways. So being closed is that it has to, or that's what's required for it to be a subspace. If x and y belong to S, then so does their sum. If x belongs to S, then all its multiples also belong to S. Okay, so once again, it is what makes it vector space. It has to be self-contained. Okay, so the algebra then exactly the same. It satisfies those eight axioms. You can do component-wise as if you are in that n-dimensional space, but the other vectors simply do not come into play. So we'll see more examples of those, and for now it will be. So lines, once again, along any line, as long as it passes through the origin, that's fairly easy to prove right here. That any line through the origin, as you can see, it was generally it's like a plus tu. Okay, so that's a line. Okay, but we're choosing not every line. We're choosing a line with the initial point at the origin. Okay, so there is no a. Okay, so tu, u is the direction vector, and t is the multiple. So you can stretch vector u forward or backwards, and that gives you the line. And therefore, if you were to do algebra, you can easily verify that. For example, here I choose to verify what I choose to verify the property number one right here. So just addition of two vectors. So vector A is tu. Vector V is SU, so two different vectors within the same space S. If I add them together, what the end result is T plus S, and then we have our vector, which also happens to be a multiple of U. So if you have two multiples of U, add them together, is it the multiple of U? The answer is yes. Okay, so that proves that my line is closed, as that's the language once again, closed under vector algebra. So number one operation, number two operation is scalar multiplication. If I have a multiple of U, okay, and I multiply it by another number, so it's still multiple of U. Okay, that's what it says, and so that naturally, once again, it belongs to space S, and so that way we prove that indeed any line that passing through the origin is a vector space or a subspace in this. Okay, so that is the main examples. They're naturally every vector space, Rn say, has so many subspaces that it's hard to even point out. This example shows you that every line in any space, it doesn't have to be a plane. As you can see, the algebra is entirely dimensionless, right? So the algebra is entirely carried out in terms of just plus minus as in following nothing, but we followed here the axioms. So we are not carrying out operations component-wise, anything like that. We don't have to. As you can see, it's entirely defined. Everything is done with axioms, so letters, whatever the dimension is, does not even come up. And therefore, so whatever we say about all the vector spaces we can think of. If we only using axioms, then only the axioms matter, and then that's what literally a vector space is. It's anything with operations that, where's my definition? With operations that satisfy the 8 axioms. Okay, that's all. So that demonstrates that every multidimensional space has a bunch of subspaces, all the lines. But also, once you go to the next level, you also all the planes too. And all three-dimensional spaces, four-dimensional spaces. So then you have every Rn will have Rn minus 1, many, and then on and on. You go to R3, R2, R1, all of these here. And once again, each of them is many. Just this many we just saw are one being the line, and there are infinitely many of them present. So the same with every other dimension. Okay, so all right, so okay, so let me point out. So for the test, okay, so I don't want to go too deep here. So I just want to give you the cutoff place. Yeah, I guess the this end of the section here somewhere. Okay, so just the beginning. So not the axioms as much. Just the basic things about the vector algebra. So this test, not test. Okay, so I'll stop here, I think. So any questions about it? Okay, so I'll see you next Tuesday.